Have you ever just stopped and wondered how our digital world, well, how it works? I mean, how does your favorite app, or your online bank, or even your cloud storage just stay so reliable, even when things are breaking behind the scenes? It turns out it's all governed by a hidden set of rules about a really simple concept: truth. And to get our heads around it, let's start with a question you've probably never even thought to ask.
Seriously, think about your bank account. You could be pulling cash from an ATM in Tokyo, checking your balance on your phone in New York, and then get a deposit notification while you're in London, all within minutes of each other. How in the world does the system make sure that every single one of those actions is looking at the exact same up-to-the-second correct balance?
And that right there, that's the core challenge. We're talking about what are called distributed systems, basically just networks of computers that all have to agree on one single source of truth. But what happens when the network connection between them gets flaky, or one computer just starts running slow? How do you keep that single, reliable truth from falling apart?
Well, for a long time, the answer to that question was guided by this foundational idea that forced a really tough choice on everyone. It's called the CAP theorem, and it basically lays out an impossible triangle for anyone trying to build these systems.
So the theorem says a system can only promise you 2 out of 3 absolutely critical things. First, there's consistency, which just means everyone sees the same, most up-to-date data. Then, there's availability, meaning the system actually responds when you ask it for something. And finally, there's partition tolerance, which is the system's ability to keep on chugging even when the network splits and computers can't talk to each other. It's exactly like that old saying for projects: good, fast, cheap, pick 2. This is the data version.
Now here's where it gets really interesting. You can pick consistency and availability, but you're gambling that your network never ever breaks. Or you could have consistency and partition tolerance, but that means sometimes you just have to tell a user, sorry, can't help you right now, try again later. Or you go with availability and partition tolerance, but then you might be showing someone data that's a little bit stale. And here's the thing, for any big system on the internet today, you can't sacrifice partition tolerance. It's not a choice. Network partitions are just a fact of life. So for years, the real, painful choice was always between consistency and availability.
And this is a great twist. About 12 years after he came up with it, the creator of the CAP theorem himself stepped up and said, you know what? That simple pick 2 rule, it needs a serious update.
Yeah, in 2012, Eric Brewer wrote this amazing retrospective, basically saying that this black and white choice was just too simple. The real world of building systems is so much more nuanced, and the goal isn't just to pick a side and stick with it. It's about intelligently managing these trade-offs.
Brewer's big insight was this: why design your entire system around an event that, yeah, it's going to happen, but it's actually pretty rare? Most of the time, the system is working perfectly fine. So why would you permanently sacrifice either consistency or availability? He argued that the real goal should be to get as much of both as you can, and just have a really smart plan for what to do during those brief moments when a partition actually happens.
Okay, let's make this super real. Picture yourself at an ATM, but its connection to the main bank server is down. The system is partitioned. Now, according to the old rigid CAP rule, that ATM should either refuse to give you money to stay consistent or risk you overdrafting. But that's not what happens in real life, is it?
And this is just brilliant. It perfectly shows the modern way of thinking. The ATM temporarily chooses availability. It goes into this special stand-in mode and lets you withdraw a limited amount of cash, say $200. It's making a bet, knowing its data might be a little inconsistent for a while. Then, later, when the connection is back, it syncs up and restores consistency. And if a mistake was made, like it let you overdraft, it has a plan to compensate, probably by charging you a fee. See, it's not about choosing C or A forever. It's about managing that trade-off on the fly.
This whole new way of thinking led to an even more sophisticated model, one that considers another really important question. What happens when the network is perfectly fine? Which, as Brewer pointed out, is most of the time.
So this brings up a new question, right? If there's no network partition, what's the trade-off you're making then? This is where a principle called PACEL-C comes into the picture. It basically extends CAP to think about the system's normal, everyday operating state.
Okay, PACEL is a bit of a mouthful, I know, but the idea is incredibly powerful. It just says, if there's a partition, you have to choose between availability and consistency. That's the CAP part. Else, meaning when everything's normal, you face a totally different choice, the trade-off between latency and consistency. In other words, you're trading speed for accuracy. Do you give a user an answer that's super fast but maybe slightly out of date? Or do you make them wait a little longer for the absolute guaranteed to be correct data?
So we have these high-level principles like CAP and PASL to guide us, but how does a group of computers actually achieve consistency? I mean, how do they physically all agree on what the truth is? This whole problem is known as consensus.
For decades, the gold standard for getting computers to agree on things was an algorithm called Paxos. The only problem, Paxos is famously, mind-bendingly difficult to understand, let alone implement correctly. So in 2014, some researchers introduced Raft, an algorithm that was designed from day one with a single goal in mind: understandability. It solves the exact same problem as Paxos, but in a way that regular developers can actually build and feel confident about.
Raft works using this really beautiful, simple process. First, all the computers, or nodes, in the system hold an election to pick a single leader. Just think of it like a group of friends trying to decide where to get dinner. You pick one person to make the final call. Second, every change has to go through that leader. The leader writes it down in its log and then tells all the other follower nodes to update their logs to match. Once a majority of them have the change, it's locked in, it's permanent. And finally, a bunch of strict safety rules make sure that once a decision is made, it can never, ever be reversed.
Okay, so let's bring all of this home. We've journeyed from the rigid CAP theorem to the much more flexible PASL principle, and we even have practical tools like Raft to actually make it all happen. So, how does this actually play out in the systems we use every day?
Well, it all comes down to this. Designing these massive systems isn't about following one single rule. It's about navigating a whole spectrum of choices to build something that fits a very specific need. There's no one best system out there, only the right set of trade-offs for the job you're trying to do.
And you can see this in the real world with databases you've probably heard of. Take a look at Cassandra. Its classification is PA/EL. That means during a partition, it chooses availability, and else, in normal times, it chooses low latency. It's built for speed and being online no matter what. That's perfect for something like a social media feed, where you'd much rather see something slightly old than see nothing at all. Now compare that to a classic database like PostgreSQL. It's PC/EC. It will always pick consistency every time, even if it means sacrificing availability or speed. That's why it's trusted for things like financial transactions. And then you even have hybrids like MongoDB, which makes different choices in different situations.
And this brings us right back to Eric Brewer's main point. The goal today isn't about picking two things and throwing the third one away. It's about being a smart architect, about designing a system that actively manages all these tensions to deliver exactly what the user needs, at the moment they need it.
So, that leaves us with one final thought to chew on. In this always-on world we all live in, what's ultimately more important? Getting a response right this second, even if it's not perfectly up to the millisecond correct, or waiting just a little bit longer for the absolute verifiable truth? The answer, as we've seen, really depends on what you're trying to build.